Hello everyone, I hope you are doing well. This is Satyam Agrawal, your instructor for this course, and today we are going to study about the Coulomb's law, which is the fundamental law of electrostatics. And this is class 12th physics for CBSE, ICSE, JEE Mains and JEE Advanced. So let's move on. So what will you learn today? By the end of this lecture, you will master the core concepts of electrostatic force, that is the nature and the behavior of forces between charges, the mathematical statement and the formula, and how force depends on Q1, Q2 and R. We learn about the vector form, that is the direction and the superposition principle, and then we learn about the permittivity, that is the medium effect and relative permittivity. So before moving on to the Coulomb's law, let's revise what we studied earlier. Let's have a look on the properties and principles of the electric charge. So first of all, we learnt about the conservation of charge, which is that in an isolated system, the total electric charge remains constant and the charge can be transferred between objects and materials but can never be created or destroyed. So the total charge before will be equal to the total charge after any interaction. So we also saw some real world examples, that is two identical spheres touching each other and charge redistributes equally and so on. Also, we learned about the quantization of charge. That is, the charge exists only in integer multiples of elementary charge E equals to 1.6 times 10 to the power minus 19 coulombs. Okay, where n is the integral multiples, that is 0, 1, 2, or minus 1, minus 2, and so on. Okay, whereas at macroscopic levels, the quantization is negligible and the charge appears to be continuous. Moving on, we studied about the additivity of charges, that is the algebraic sum rule, which states that the total charge of a system is the algebraic sum of all individual charges. So signs matter here. So Q total will be equal to Q1 plus Q2 plus Q3 and so on. So unlike mass, charge is a scalar quantity but carries a sign, that is positive or negative. We can see an example such as there are three charges, 2 microcoulombs finds 5 microcoulombs and plus 3 microcoulombs, and when we add that, the total is 0 microcoulombs. That implies that the system is electrically neutral overall. Okay. Now we also studied conductors versus insulators. So there are several properties. You can just have a look and go through them. It can be asked in multiple choice questions in your CBSE as well as in your JEE Mains examination. Moving on, as I told you, we'll be studying semiconductors in detail later on in class 12 physics. Then we saw some examples such as balloon on hair, foam and paper, the gold leaf electroscope, lightning, etc. Okay. So there are common misconceptions that you must keep in mind, that current creates charge. The truth is that the current is the flow of existing charge. Charge carriers are the electrons which already exist in the conductor only. The second misconception is that the charge can disappear. So the truth is that charge is conserved. It may neutralize locally, but total charge in an isolated system never changes. And the third misconception is that the protons move in circuits. Okay. Whereas in metallic conductors, only electrons move. Protons are locked in the atomic nucleus. So you must keep this in mind. Now, these are some practice problems. There are three kinds of problems. You can just solve them and reply in the comments the answer to these problems, and I will just verify those answers and will reply you back. Okay. Now, this is the summary of the electric charges, whatever we have studied till now. You can just take a screenshot, or maybe if you are taking notes, then that's well and good. Now let's move on to our agenda today, which is the Coulomb's law. So first of all, let's see some historical context, that how do charges interact without touching. So in 1785, a French physicist, Charles-Augustin de Coulomb, answered this question using a brilliant simple device called the torsion balance. By suspending a charged sphere on a thin fiber and bringing another charged sphere nearby, Coulomb measured the twisting force and established the first quantitative law of electrostatics. Okay. So this is the Coulomb's torsion balance, as you can see in the pictures. This scientist was a masterpiece of experimental physics, the precise, elegant, and revolutionary. So this is the torsion wire, which is a fine silver wire that twists proportionally to the applied torque, enabling precise force measurement. Then there are these charged spheres. There are two small conducting spheres charged by contact, one fixed and one on the balance arm. So this is charging by induction. and then a measuring force. The angle of twist directly indicates the electrostatic force. Okay. So the Coulomb varied the distance and the charge system. Now talking about the statement of the Coulomb's law. Okay. So the Coulomb through his experiments found out that the two charges Q1 and Q2 kept at a distance r in a medium, okay, exerts a force F on each other, and the magnitude of the force F is given as F is equal to K multiplied by Q1 into Q2 upon R square. So this law gives the net force experienced by each of the charges Q1 and Q2. This law also accounts for the surrounding medium in which charges are submerged. So in this equation, K is the electrostatic constant which depends upon the surrounding medium. About electrostatic constant K, we will discuss further in detail. So this is the complete formula. Okay. For free space, we take the value of K as 9 into 10 to the power 9 Newton meter per Coulomb square. Okay. So also we can write K as 1 upon 4 pi epsilon naught. So the force F acts along the line joining the two charges and is repulsive if Q1 and Q2 are of same sign, and is attractive if they are of the opposite sign. Okay. So here F is the electrostatic force, Q1 and Q2 are two charges in coulombs, R is the separation between those charges in meters, whereas the epsilon naught is the permittivity of free space. Moving on, let's talk about the Coulomb's constant. K is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So this enormous value tells us the electrostatic force is incredibly strong at small distances and far stronger than gravity. So the unit is force into distance square per charge square. Okay. And the origin is derived from the epsilon naught, which is the permittivity of the free space. Okay. Moving on, the nature of the electrostatic force. So let's take the first case. This is the case one where these are like charges, both positive or both negative. So as we know that like charges repel each other, whereas in case 2, there are two unlike charges, that is the negative and the positive, or the positive and the negative. So we also know that the unlike charges attract each other and like charges repel each other. So what are the key rules? Like charges plus and plus or minus and minus repel each other, and unlike charges positive and negative attract each other. So force acts along the line joining the two charges, and the force is a Newton's third law pair, equal and opposite. So the force is always mutual, that is F12 is equal to minus F21. Okay. Moving forward, the vector form and the superposition. So the vector form is given as F12 having a direction is equal to K Q1 Q2 by R square, okay, or 1 by 4 epsilon naught K Q1 Q2 by R square into R vector, okay. So here R hat is the unit vector from Q2 to Q1. The sign of Q1 Q2 determines the direction automatically. Talking about the principle of superposition, when multiple charges are present, the net force on any charge is the vector sum of individual forces. So the net force vector would be equal to F1 vector plus F2 vector plus F3 vector and so on. So add forces component wise, and we never add them as scalar quantities. So the first thing would be identifying the forces. We will list all the forces on the target charge. Then we will resolve their components, break each force into x and y components, and then we will take their vector sum, that is we'll add the components to obtain the net force. So you should apply this three-step method systematically for any multi-charge configuration. Okay. So what were the key takeaways from this lesson? We learned the formula of the electrostatic force, which is K Q1 Q2 by R square, and the unit was force, the force was inversely proportional to the charge product and 1 by distance square. What were the nature of those charges? Like charges repel each other and unlike charges attract each other. And force is mutual and central. That is, let me write it once again. So F1 vector would be equal to minus F2 vector. Okay. Suppose this is a charge Q1 and this is the charge nu2. This is the F1 vector, and this is F2 vector. So F1 vector is equal to minus of F2 vector, okay? So you must keep this in mind. Now, medium. In a medium, force reduces by a factor of K, which is 1 by 4 epsilon naught. And it is the relative permittivity of the free space. And talking about the superposition, we learned that the net force is the vector sum of all individual forces on a charge, okay? So, talking about the vector form of Coulomb's law. Now, Coulomb's law in vector notation captures both the magnitude and direction of the electrostatic force between two point charges. Okay, so F12 vector is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square R hat 12. So R hat 12 is the unit vector pointing from charge 1 towards the charge 2. So as we know that the like charges repel and unlike charges attract along the line joining both of these charges. And so the magnitude will be F is equal to 1 by 4 pi epsilon naught magnitude of Q1 Q2 divided by R square, which is always a positive quantity. Moving on, what is the effect of medium on electrostatic force? So what we say, when two charges are placed in vacuum or when the same set of charges are fully submerged in a medium, the net force experienced by the charges will be different. The effect of presence of medium is accounted in the proportionality constant K. The electrostatic constant K is defined as 1 by 4 pi epsilon naught, where epsilon naught is 1 upon 4 pi in CGS system. Okay. So epsilon is the absolute permittivity of medium and epsilon naught is called the permittivity of free space, which has a constant value given as epsilon naught is equal to 8.85. Let me just write that. Epsilon naught is equal to 8.85 multiplied by 10 to the power minus 12 Coulomb square per Newton meter square. Okay, so you must keep this value in mind, which is very important, that epsilon naught, which is the permittivity of the free space, equals 8.85 times 10 power minus 12 Coulomb square per Newton meter square. So when we talk about epsilon r, okay, epsilon r is equal to epsilon by epsilon naught. And epsilon r is called the relative permittivity of medium with respect to the free space, and it is also termed as the dielectric constant and is given as epsilon r is equal to epsilon by epsilon naught. So for free space, epsilon r is equal to 1, okay, as here mentioned, it is equal to 1, and k is equal to 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So we can say when any two charges are placed in vacuum, okay, or air, the force experienced by the charges can be given as force in the air is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. So when these charges are submerged in a medium having dielectric constant epsilon R, then force becomes force in a medium, okay, is equal to force in a vacuum divided by K. So as K increases, the force decreases, okay. So conductors effectively have K upon infinity, no net electrostatic force can exist inside them, okay. So what happens is, if medium is always smaller than the force experienced in the air or in a vacuum. So because the epsilon r is always greater than 1, so we can write force in a medium is equal to Okay, this implies that force in a medium is always smaller than force in air. Okay, and why? Because epsilon r is always greater than 1. Okay, so you must keep this in mind. So as per this analysis, we can state that in a medium, force experienced by charges q1 and q2 decreases, but it can also be stated that the net force which q1 is exerting on q2 remains same no matter in whichever medium charges are placed. This is because medium does not affect the force q1 that is exerting on q2, but due to both of these charges, medium atoms get polarized, and the polarized atoms or dipoles in the medium exert another force on these charges which is always in opposition to the force between the two charges in free space. That is why in a medium, net force between two charges is always less than that compared to free space. And Coulomb's law gives this net force, and as already explained, that electrostatic constant K or the dielectric constant of medium in it accounts for the effect of the medium on the net interaction between the two charges. So, as analyzed and explained, the net force between the two charges decreases when the charges are submerged fully in a medium at same separation. So, the force may also increase if medium exists only between two opposite polarity charges and not occupying the whole surrounding of the charges. This can be easily explained. Let me just explain that to you using a figure. Just allow me a moment. Now, look at this carefully. Suppose this is a dielectric slab, okay? This is a dielectric slab. Now there is a force F1 in this direction and another force minus F2 or F1 in this direction. Okay, what is this? This is a dielectric slab. Okay, and now there are two charges Q1 and Q2. These are the two charges. So this is exerting a force here, and this is also exerting. So what is happening? Dipoles or the polarization. So these dipoles are created and are polarized, as we discussed yesterday during conduction of an isolated conductor in a metallic and non-metallic body. Okay. So as shown here, if there exists a dielectric slab between two charges, then we can see that the both charges being of opposite polarity attract each other, say with a force F1, and both of the charges will polarize the medium dipoles on the facing slab of the dielectric as shown in this figure, and due to which these dipoles will exert an attractive force Fm. Okay, on these charges. So this is a force Fm. Fm. This is not here. It's here. Okay. Now when Fm is exerted, so arrow is here. So on these charges in the same direction of F1, and this increases the net force on the two charges. So similar to this, we can easily prove and explain that if a dielectric slab is inserted between the two same polarity charges, then the net force between the two charges decreases as shown in this new figure. Now I have changed the direction of the arrows. Okay. And here now will be plus minus, okay, plus minus, okay. Then the net force between the two charges decreases as force by the medium on the charges acts in opposite direction to the force F1 between these charges. So we can state that on inserting a dielectric slab between two point charges, the net interaction between the charges increases if the charges are of the opposite sign, and it decreases if the charges are of the same sign. Okay, moving on. Now there are three simple problems. Okay, first of all, we'll discuss a board level problem which states that find the force between Q1, which is equal to 2 microcoulombs, and Q2, which is equal to 3 microcoulombs, separated by R is equal to 0.1 meter in air. So we are given the values 2 into 10 power minus 6 coulombs. So mu is equal to 10 to the power minus 6. And then we are given Q2, which is equal to 3 into 10 to the power minus 6 coulombs, and our radius is given as 0.1 meters. Okay, so we'll apply the Coulomb's law. F is equal to K. K is equal to 9 into 10 to the power 9. Okay, multiplied by 2 into 10 power minus 6 into 3 into 10 power minus 6 upon 0.1 square. So when you calculate this, you will get the answer as 54 into 10 power minus 3 upon 0.01, which is equal to 5.4 Newton, and the force would be repulsive as both of the quantities are positive. Okay. Now let's see a JEE Mains level problem which states that two charges Q1, which is equal to 5 microcoulombs, and Q2 minus 3 microcoulombs are 0.2 meter apart in a medium with dielectric constant K is equal to 2, and we are supposed to find the electrostatic force. So step-by-step solution is given that the force in the medium will be equal to K into 5 into 10 power minus 6 into 3 into 10 power minus 6 upon 0.2 square, which is equal to 3.375 newtons. Then we'll apply the medium correction. So the force will be given as permittivity in free space force naught upon K, which is 3.375 upon 2, which is equal to 1.69 Newton. And since the charges are unlike, they will attract each other. So the force is of attractive nature, which is 1.69 Newtons. Okay. Now let's see a JEE Advanced level problem. So there are three charges. QA is which is equal to QB equal to QC is equal to 1 microcoulomb at vertices of an equilateral triangle. Side 0.1 meter. Okay. So we are supposed to find the resultant force on QA. Suppose FAC, that is force on force on A, charge A from C alongside AC away from C at 60 degrees. Okay. And force on A from B alongside AB from B, and F net, that is the vector sum bisecting the 60-degree angle between force on A due to B and A due to C. Okay. This is A, B and C. So by symmetry, force on A from B, force on A from B and force on A from C, okay, which is equal to 0.9 Newton at 60 degrees. The resultant bisects the angle. Okay, so force on A from C and force on A from B, then the net would be bisecting the 60-degree angle between force on A due to B and force on A due to C. So the net force will be 2F into cos of 30 degrees. So since it is bisecting, it would be 60 degrees divided by 2, which is equal to 30 degrees. So 2 into 0.9 Newton multiplied by cos of 30 degrees given as root 3 by 2. Okay. So it is equal to 1.56 Newton. So you can solve this, and if you still have any doubts in this problem, you can always mention in the comment and I would be more than happy to solve your doubts. Okay. So principle of superposition. So what is the principle of superposition? When a charge is acted upon multiple charges, okay, the net force is the vector sum of all the individual Coulomb forces. That is, net force vector is equal to F1 vector plus F2 vector plus F3 vector and so on. So this is the vector addition. We'll be adding forces as vectors, resolve them into components and then combine. And in the independent forces, each pairwise force is unaffected by other charges present. Okay. So this is universally applicable for any number of point charges, which is the foundation of electrostatics. So what are the common mistakes that can be avoided? Ignoring the charge sign. Sign determines the attraction versus repulsion. So we always use signs for direction, magnitude for force value. So in your class 12th board examination, suppose you resolve into components, get the final answer, but you are not describing whether the charge is attractive or repulsive, minus half marks should be deducted, okay? Then wrong units. We must always convert mu, that is the microcoulombs, to coulombs multiplying by 10 to the power minus 6, okay, and centimeter to meters for the radius before calculating. Also, we must know that the force follows the inverse square law, so we must always square the distance, okay. Now wrong direction. So the force acts along the line joining the charges, so we must use the unit vectors whether in 2D or in 3D. Now skipping medium correction. So in a dielectric we must divide by K. So the force is given by F naught by K, that is the dielectric constant of a medium. Okay. Moving on. Let's do a quick revision. We learned the Coulomb's law, which is F is equal to 1 by 4 pi epsilon naught, that is K, into Q1 Q2 by R square. Then we got to know the value of K, which is 9 into 10 power 9 Newton meter square per Coulomb square. Then we learned the vector form, that is F vector is equal to K Q1 Q2 by R square into unit vector R. And then we saw the medium effect, that the force in a medium is equal to force in free space or the air or vacuum upon K, that is the dielectric constant. Then we saw the superposition, that is the net force vector is the sum of all the individual forces with their respective directions. So in the next lecture, we will see the principle of superposition and continuous charge distribution in detail. So I hope you enjoyed this lecture and all the concepts were cleared. And still, if you face any doubts, please do connect with me on my WhatsApp number, which is 935487770. You can always message me or call me. Please call me between 6 to 7 p.m. Okay. I'll be able to answer your calls, or you can always drop me a message at any time and I would be more than happy to resolve your doubts.